Today we tell you a story. Coronary bypass. Bypassing the thrombosed coronary artery by anastomosing the internal mammary artery to its distal element had been developed and was a highly successful operation for heart attack. So, this is the ear, and this is a superficial temporal artery. And in a stroke patient, this middle cerebral artery here has become thrombosed. So they anastomose the anterior branch of the superficial temporal artery to the terminal branch of the middle cerebral artery, and on angiography there was a beautiful restoration of circulation. The operation took off and it was started in many centers. So this is what is called as plausibility. That means if one artery is thrombosed, if you bypass the circulation by another equally thick artery, it should help. But then there came a time when hundreds of patients had been operated that they started testing, did it help? So there was a randomized controlled trial comparing operated and non-operated patients and determining mortality in them. It was a multi-center randomized controlled trial costing about $12 million. And the results are here. Out of 100 operated patients, 42 died. And out of 100 non-operated patients, only 7 died. So the risk of dying in the operated group was 42 upon 100. And the risk of dying on the non-operated group, this one, was only 7 upon 100. That means 6 times more patients died if operated. The operation was stopped and the should help theory failed. And there was a paradigm shift in choosing which treatment to give. So there was a paradigm shift in modern medicine where the should help was rejected, plausibility was rejected, and there was an emphasis on did it help. That means counting numbers became important, especially when you are choosing a treatment for the patient. Very sad. Your divorce with maths, which you said bye-bye to after class 10, now stands reversed. You may cry, you may fume, but you will have to start understanding numbers. So you have to become good users and producers of research by creating correct numbers, interpreting correct numbers, and understanding those numbers in research papers so that you can keep updated. You don't choose treatment on biological plausibility, but on what did happen, as reported in research. So what do we do research on? We do research on what is called as the event of interest. What is interesting? That which can cause pain or pleasure. So pain or pleasure to you, or pain or pleasure to the community of which you are in charge. So The model that we are studying in medicine is the healthy is becoming diseased, disease is becoming cured, disabled, dying, or there is loss to follow. Only becoming cured is pleasurable. All the others, healthy to disease, disease to disabled, dying, or loss to follow up, all are red arrows. The red arrows have to be braked, and the green arrows have to be accelerated. And therefore, you have to study factors which affect these arrows, and you have to be able to measure the magnitude of these arrows, because these arrows are simply transition rates. At what rate is the transition occurring from healthy to disease, or from disease to death? So let us understand this jar which has 100 cc's of 100 cc's capacity, and there is 10 cc of fluid in it. That means 10 out of 100 are diseased. Now it is filling at the rate of 2 per day, and it is emptying at the rate of 1 per day. How many would be there, or what would be the level of the fluid at 10 days? So 2 minus 1, that means 1 per day increment, and in 10 days there should be 10 more. 10 were there from before, 10 more means 20. So you have understood incidence rate, you have understood attrition rate, and you have understood prevalence at time 0, 10 upon 100, and prevalence at time t, that is 20 upon 100, and therefore this calculation is that Pt is equal to prevalence at time t is equal to prevalence at time 0 plus incidence rate minus attrition rate into time. This formula you must remember, so that you are able to estimate how many people in your population of interest are in that particular state, and at what rate is the status changing. And this model around which you work is called as Markov model. It was discovered by a Russian scientist, and this is called as Markov modeling. So even in the COVID pandemic, Markov modeling is extremely useful for planning what resources to put where. So after this little bit of mathematics, we must understand that if attrition rate is 0, for example, patient is becoming diabetic or having cancer, then is unlikely to be cured. Then the same formula, the IR minus AR will become IR. So if attrition rate is 0, then you can determine incidence rate by knowing prevalence in the population of a condition at 2 times, PT and P0. So, studying the event of interest. Now let us concentrate on how to study this event of interest, which is causing pain or pleasure to our population. Let us imagine that it is acute respiratory distress syndrome following fever, as in the COVID pandemic. So the first thing that you have to find out is that what is epidemiology? Epidemiology is the distribution and determinants of disease, of the event of interest. So the distribution is time distribution, when, place distribution, where, person distribution, in whom the event of interest occurred. And then you have to find out why did it occur. So what, when, where, why, and how. and then what. So the 5 W's are what, when, where, why, and then what. What to do? So you will have to modify the brakes and the accelerators of the transition rates. And that will form the strategy to deal with the event of interest. So, study of time, place and person distribution is descriptive epidemiology, and studying the factors affecting transition rates they are called as causes, and these is called as analytical epidemiology or causality studies. In medicine, if the cause is etiology, effect is disease. If the cause is prognostic factor, effect is outcome. And if the cause is treatment, effect is result. In etiological factor and prognostic factor, we are just observing, we are not doing anything. But in the treatment, we are intervening. Therefore, the responsibility of the researcher, ethical responsibility of the researcher, is very much enhanced if it is an intervention study. And such studies, which are intervention studies, are called as experimental studies, and where you are only studying etiological factor and prognostic factor, where you are only observing them, they are called as observational studies. All right. So, then comes the question of studying the unit of the study, studying the person concerned. You want to be very, very sure whether the event of interest is present or absent. And anything that tells you 100% sure is called as gold standard. For example, if you do a biopsy, you are sure of which cancer it is. Biopsy is a gold standard in cancer. But biopsy is maybe costly, maybe unacceptable, because it is a lot of intervention and pain. Therefore, you have to find out surrogates for the gold standard. And that surrogate is more doable, less costly, less risky. And you have to validate that surrogate against the gold standard, and such studies which validate the surrogate against the gold standard are called as diagnostic strategy studies. Now, we have told you when, where, in whom, what is occurring, why and how, and then what. We have told you that this is the paradigm of the community medicine about the event of interest. So what will you do? You will first take a sample from the population, collect data on it. And what is data? Data is a collection of variables. What is a variable? Variable can vary from case to case. For example, in each one in this class, the height can be different. So variable is that which can vary from case to case. At the end of it, for your study population, you'll make a master chart, which is usually in the Excel. And the first row contains variable name, and the rest of the rows contain the variable values. The variable name and the variable values, and if you see name is nominal. It is name. Same way, sex is categorical. It is telling you category. Age is numeric, is a number. And this number is continuous because it can be 5 years 3 months or 5 years 4 months. So there can be a decimal there. So where there is a fraction, it is a numeric continuous variable. And where there is no fraction, for example, number of people in the class or number of persons who got well, That is a numeric discrete variable. Then you have how much you need sugar, 1 plus, 2 plus or 3 plus. This is an ordinal variable. 3 plus is more than 2 plus. But 1 plus and 2 plus do not make 3 plus. So that is an ordinal variable. And then there are ratio variables. For example, how many diseases got well by this treatment? 20% with treatment A, 30% with treatment B. So that percent where you have a denominator is a ratio variable. So the types of variable are nominal, categorical, ordinal, numeric continuous, numeric discrete and ratio. And you must remember these. Now we are starting to deal with summarizing the column in the master chart. And we are starting with the numeric variable. So there is a central tendency of that numerical variable, the central number, like mean, median or mode. Mean is sum up everything divided by the number, total number of observations. Median is 50% below, 50% above. And mode is the number with the highest frequency. But central tendency doesn't work. Central tendency doesn't work. It must have a range. So this range or dispersion, how are the numbers dispersed around the central tendency? That is called as dispersion. So one is the lowest and the highest, that is range. Then there are 25% below this and 25% above it. So this is the 25th percentile and this is the 75th percentile. This is called as interquartile range. And then there are confidence intervals. For example, 95% confidence interval means that 95% of the observations are from in this segment, lowest to highest. So 95% confidence interval is that 95% you are confident that the value will range from this lowest to this highest. Okay. Then there is standard deviation. And normally there is a relation between standard deviation and confidence interval. So mean plus minus 1 standard deviation is equal to 68% confidence interval if the distribution is normal. Mean plus minus 1.96 standard deviation is equal to 95% confidence interval, and mean plus minus 3 standard deviation is equal to 99% confidence. So this is the relationship between confidence interval, one measure of dispersion, and standard deviation. If the curve is normal, that means the decreasing frequency on the left and the right side are symmetrical, then you can talk about standard deviation. But if it is skewed, the curve is skewed, it is like this, then you talk of confidence interval. For categorical or ordinal variables, for example, you have grade 1, 2, 3 or 4 osteoarthritis you are trying to measure by the X-ray of the knee. And supposing 10 were in grade 1, 12 in grade 2, 9 in grade 3, 9 in grade 4. So this number is called as frequency. Divide this number by total, 10 about 40, it becomes relative frequency. And as soon as you can see this, so this relative frequency of grade 1 osteoarthritis in your study population is the probability of grade 1 osteoarthritis in your source or target population. So by just adding a denominator, you are able to make this result generalizable. It will apply in a population which has not been studied. And therefore, this is a statistic, and by the statistic you are trying to estimate a parameter which has not been studied. And the art of estimating the parameter by the statistic is called as statistics. All right. Now this is the cumulative frequency. So 10 upon 40 is grade 1. But 10 plus 12, that means 22 upon 40 is grade 2. By the cumulative frequency, you can say that 22 out of 40 were below grade 2. So this is a cutoff. And this is limited to that grade only. Relative frequency is limited. Relative frequency is limited to that grade only. But cumulative frequency is a cutoff. Okay. So I have said that relative frequency in the study population, 10 upon 40 for grade 1, is the probability in the target or the source population. So I have given you a concept of a study population and a source population from which it is being derived or drawn, and then the results of this study population are being applied to the target population, which is coming from the same source population. Now, so this is what I told you, that 10 out of 40 is the relative frequency of grade 1 osteoarthritis in your study population. So 10 out of 40, that means 0.25, will be the probability of grade 1 osteoarthritis if you would have studied the entire source population, the universe. So this is the parameter, and you are estimating this parameter by the relative frequency. Relative frequency in the study population is the probability in the target population. So what are you basically doing? From the source population, you are taking a study population, and from the study population, you are finding out the result, and you are assuming that this result will apply to the target population, and this is called as external validity or generalizability of the result. And this is possible if the sample, the method of sampling from the source population, the study population, the way it is selected is called as sampling. And if the sampling is correct, that means the frame is correct and the size is correct, then the results of your study will apply to the target population. The statistic will apply to the parameter in the target population. Now, the best way to sample is random sampling, where every person in the population has an equal probability of selection. Second can be stratified sampling. For example, if these were males and these were females in the source population, then you must select males and females in the same ratio. Males and females in the same ratio that were present in the target population. So this is strata male, this is strata female, and you must random sample from both. And the proportion of these numbers would be the same as in source population. So that is called as stratified sampling. The third way is that you take clusters, cluster A, B, C from the population, from the cloud of the universe, okay, from all mohallas of Lucknow. And there's a theorem which applies to this, which is called as central limit theorem. And if the results in cluster A, B and C are R1, R2 and R3, then the mean in the population will be the mean of R1, R2 and R3. And the standard deviation in the population will be standard error is equal to standard deviation in the population will be equal to standard error upon root n, where n is the size of cluster. Now let us apply it to a causality study. So I told you that there are 4 quadrants in this 2x2 table. Intervention positive, dead, alive. Intervention negative, dead, alive. So there are 4 quadrants. So these are the 4 quadrants in the study population. And these are the 4 quadrants in the source population. So A, let me draw it here. You must take the study population in a manner that A, B, C and D. A upon A, B upon B, C upon C and D upon D must be equal. And that is only possible if you have done a random selection, because in random selection, drawing from random selection over a sufficient sample size, you can rest assured that this will be the status where A upon A will be equal to B upon B, will be equal to C upon C, will be equal to D upon. So now let me tell you how to choose the sample size, how to do a random selection and how to choose a sample size.